Good morning, teachers, and all my dear friends. Today, I, Jyoti of class BSc Chemistry Honors first year, is here to prepare a audio lecture for the visual impaired candidates. So here we are going to start with the organic first chapter, that is alkenes, and this chapter is taken from the Pradeep's publications book. Now let's start from the first topic, that is introduction. Unsaturated aliphatic hydrocarbons containing two hydrogen atoms less than the corresponding alkenes and which are characterized by the presence of a double bond in their molecules are called alkenes. These are also called olefins. Since the lower member of this class, like ethylene, form oily products on reaction with halogens such as chlorine and bromine. Their general formula is CnH2n, where n is equals to 2, 3, 4, etc. Unsaturated hydrocarbons containing 2 and 3 double bonds are also known. They are called alkenes and alkatrines respectively. The general formula of alkenes is CnH2n minus 2, where n is equals to 4, 5, 6, etc. And that of alkatrines is CnH2n minus 4, where n is 6, 7, 8, etc. The term polyene is used for unsaturated hydrocarbons containing several, usually more than 4 double bonds. Next topic is nomenclature of alkenes. Alkenes are named both by their common and IUPAC names. First is common system. In the common system, unsaturated hydrocarbons containing a double bond called olefins. The name of an individual olefin is obtained by replacing the suffix "ane" from the name of the corresponding alkane by "ylene." That is, common names alkane plus ylene is equals to alkyne. In case of isomeric olefins, the position of the double bond is indicated by Greek letters alpha, beta, gamma, and delta, etc. The numbering being done from a direction which gives the lowest Greek alphabet to the carbon atom carrying the double bond. Sometimes prefixes such as iso are also used for the branch chain isomer. Second is IUPAC system. The IUPAC system, the unsaturated hydrocarbons containing a double bond are called alkenes. The name of the individual alkene is derived by replacing the suffix "ane" of the corresponding alkane by "ene." That is, IUPAC name is equals to alkane plus "ene" is equals to alkene. The following rules are generally followed while naming alkenes according to IUPAC system. First, the longest carbon chain containing the double bond is chosen as the parent alkene. Second, the position of the double bond and the substituents, if any, are indicated by Arabic numericals, that is 1, 2, 3, etc. Numbering being done from that side which gives the lowest number to the double bond. If while numbering the chain the double bond receives the same number from either side, the carbon chain is numbered in such a way that the substituent gets the lowest number. Third, the position of the substituent separated by hyphen is either prefixed to the name of the alkane or is replaced before the suffix "ene." Fourth, the name of the substituent on the carbon chain is prefixed preceded by its position to the name of the parent alkane. A hyphen separates the position and the name of substituent. Fifth, if there are more than one substituents, each substituent preceded by its position is arranged in alphabetical order before the name of the parent alkene. Sixth, in case the same substituent is repeated twice, thrice, 4 times, etc., the prefix di, tri, tetra, etc. are attached to the name of substituent. Seventh, while deciding the alphabetical order of the various substituents, the prefixes di, tri, tetra, etc. are not considered. The common and IUPAC names of some important members of the classes are given below. Number of carbon atoms 2, formula C2H4, and common name is ethylene, IUPAC name is ethene. Number of carbon atoms 3, formula C3H6, common name is propylene and IUPAC name is propene. Number of carbon atoms 4, formula C4H8, common name is alpha butylene, beta butylene and isobutylene. IUPAC name is 1 butene, 2 butene and 2-methyl propene. The IUPAC names of some branch chain alkenes are given below. Now next is Alkenyl group. The monovalent alkenyl group obtained by removing a hydrogen atom from ethylene is called vinyl group or ethanyl group, and that derived from propylene by removing a hydrogen atom from the doubly bonded carbon atom is called propenyl group. If, however, a hydrogen atom is removed from the methyl group of propylene, the alkenyl group is called allyl group. Now next topic is methods of formation of alkenes. Alkenes can be prepared in the laboratory by the following general methods. First, dehydrohalogenation of alkyl halides, removal of the elements of hydrogen halides HCl, HBr or Hi from the adjacent carbon atoms of an alkyl halide is called dehydrohalogenation. Dehydrohalogenation of alkyl halide gives fair to good yields of alkenes and is generally carried out by heating on alkyl halide with a strong base such as sodium ethoxide or a concentrated alcoholic solution of potassium hydroxide. Mechanism: dehydrohalogenation of alkyl halide is an example of elimination reactions. Elimination reaction occur by a number of different mechanisms, but we shall discuss here only two of them, that is E2 and E1. The dehydrohalogenation of a majority of primary alkyl halides occur by E2 mechanism. Kinetic studies of this reaction reveal that the reaction follows second order kinetics, that is, the rate of the reaction is proportional to the concentration of both the alkyl halides and the base. Rate alpha alkyl halide multiply base. This means that E2 reaction is a one-step process and occurs through a transition state. As the hydroxide ion begins to abstract the proton from the beta carbon atom next to the carbon atom carrying the halogen atom, the carbon hydrogen sigma bond begins to break, a new carbon-carbon pi bond begins to form, and the leaving group, that is the halogen atom from the alpha carbon, begins to depart, taking with it the electron pair, forming the carbon halogen sigma bond as shown below. Thus, dehydrohalogenation of alkyl halide occurs by a concerted mechanism in which the carbon hydrogen and carbon halogen sigma bonds are broken and a carbon carbon pi bond is formed approximately at the same time. An important aspect of elimination reaction in which that are always accompanied by substitution reactions as well. Thus, in the above reaction, along with ethylene, some ethyl alcohol substituent product is also formed. Next is stereochemistry. Next is evidence in support of above mechanism. First, relative ease of dehydration of alcohols. Step 2 in the above mechanism involving the formation of a carbocation is the rate determining step of the reaction. Evidently, greater the stability of carbocation formed, the more easily it would be formed and hence more readily that alcohols will dehydrate. Now, since the order of stability of carbocation follows the sequence tertiary, secondary, primary, hence the ease of dehydration also follows the same sequence: tertiary alcohols, secondary alcohols and primary alcohols. Second, formation of unexpected products. It has been observed that certain alcohols on dehydration produce such alkenes in predominant amounts in which the position of double bond is not that expected from the structure of the original alcohols. The formation of such unexpected products can be easily explained on the basis of carbocation intermediates. We know that carbocations always tend to rearrange to more stable carbocations if the structure permits, either by a 1,2-hydride or by 1,2-methyl shift. Thus, in dehydration of alcohols, if the initially formed carbocation is 1 degree or 2 degree, and if the structure permits, it would always tend to rearrange to the more stable 2 degree or 3 degree carbocation before losing a proton. Rearrangement by hydride ion shift. During dehydration of N-butyl alcohol, the initially formed carbocation is N-butyl carbocation, which is primary. It undergoes a 1,2-hydride shift to form secondary butyl carbocation and before losing a proton. Second is rearrangement by 1,2-alkyl shift. Acid catalyzed dehydration of 3,3-dimethylbutane 2-ol gives the rearranged product, that is 2,3-dimethyl-but-2-ene as the major product, while expected product, that is 3,3-dimethyl-but-1-ene is obtained as a minor product. The formation of the major product may be explained by the rearrangement of the initially formed carbocation, which is secondary to the more stable tertiary carbocation, by a 1,2-methyl shift. Third is regiochemistry or orientation in dehydration. When isomeric alkenes are possible during dehydration of alcohols, the more stable, that is more highly substituted alkene is always the predominant product. The formation of these products can be readily explained in terms of the rearrangement of the initially formed less stable carbocation to the more stable carbocation, followed by a loss of proton as discussed above. Fourth is Hofmann elimination. Besides dehydrohalogenation of alkyl halides, alkene can also be prepared by pyrolysis of quaternary ammonium hydroxide. This reaction is called Hofmann elimination reaction and forms the basis of Hofmann's method of elimination of nitrogen from an organic base by exhaustive methylation. Quaternary ammonium hydroxide needed for the purpose are usually prepared from the corresponding quaternary ammonium halides by treating them with an aqueous solution of silver oxide or anion exchanged resin. Mechanism: Hofmann elimination reaction is a E2 reaction in which the hydroxide ion removes a proton and the positively charged nitrogen acts as the leaving group. Regiochemistry: the regiochemistry of Hofmann elimination reaction is different from that of most of other E2 reactions. The less substituted alkene normally predominates in Hofmann elimination as compared to more highly substituted products, Sietzef elimination from base induced elimination reactions or of alkyl halides. The exact reason for this selectivity are not well known. One probable explanation is that the transition state for Hofmann elimination has considerable carbanionic character, therefore it is not stabilized by the developing double bond and shows little resemblance with the final alkene. In contrast, the transition state for Sietzef elimination is stabilized by the developing double bond and hence resembles the final alkene. Since during E2 reaction it is the beta hydrogen with respect the leaving group which is abstracted by the base, therefore another explanation for selectivity of Hofmann elimination can be afforded in terms of acidity of the beta hydrogen. The presence of a positive charge on the electronegative nitrogen atom makes the beta hydrogen acidic, but if the electron donating alkyl group is attached to this carbon, the abstraction of beta hydrogen becomes difficult. Thus, if the quaternary ammonium salt has one methyl and one ethyl group attached to nitrogen, then the hydrogen atoms on the methyl group are more acidic than those on ethyl group. As a result, abstraction of the hydrogen atom of methyl group occurs more readily than from the ethyl group, leading to the formation of less substituted alkene. For example, 1-butene is formed as a major product when secondary butyl trimethyl ammonium hydroxide is heated. Yet another explanation is based upon steric hindrance. Since the beta hydrogens on the CH3 group are sterically less hindered than the beta hydrogens on the ethyl group, therefore preferentially abstraction of sterically less hindered beta hydrogen gives the less substituted alkenes, that is 1-butene in the above example as a major product. Next topic is physical properties of alkene. Physical state and smell. The first three members of the family, that is ethene, propene and butenes, are colorless gases. The next 11 members, carbon 5 to carbon 15, are liquids, while the higher ones are solids. Except ethene, which has a pleasant smell, all other alkenes are odorless gases. Second is melting point. The melting point of alkenes do not show a regular gradation. However, the melting point of alkenes are higher than those of corresponding alkanes. This is due to the reason that pi electrons of a double bond are more polarizable than sigma electrons of single bonds. As a result, intermolecular forces of attraction are stronger in alkenes than in alkanes, and hence alkenes have higher melting points than the corresponding alkanes. This is due to the reason that the molecules of trans alkene, being symmetrical, pack more closely in the crystal lattice than the molecules of cis alkene, which are less symmetrical. As a result, greater the amount of energy required to break the crystal lattice of trans alkene than the corresponding cis alkene, and hence trans alkenes have higher melting point than the corresponding cis isomers. Third, dipole moment. Symmetrical trans alkenes are non-polar and hence have zero dipole moment. Since the dipole moment of individual group being equal and opposite exactly cancel out each other, unsymmetrical trans alkenes however have small but finite dipole moments. The reason being that although the two dipoles oppose each other, yet they do not exactly cancel out each other since they are unequal. Both symmetrical and unsymmetrical cis alkenes are polar molecules and have finite dipole moments. The reason being that in the cases the two dipole moments are inclined to each other at an angle of 60 degree and hence have a finite dipole moment. Similarly, unsymmetrical terminal alkenes such as propene and butene 1-ene have finite dipole moments since the polarity due to the alkyl group is not cancelled by the corresponding polarity in opposite direction. Boiling point is next. The boiling point of alkenes like alkanes shows a regular gradation with the increase in number of carbon atoms. Except for the first few members, the boiling point increase by about 20 to 30 degree for the addition of each carbon. The branch chain alkenes, however, have lower boiling points than the corresponding straight chain alkenes. Amongst the alkenes which show geometrical isomerism, cis alkenes have higher boiling point than the corresponding trans isomers. This is due to the reason that cis alkenes being polar have stronger dipole interaction, while trans alkenes being non-polar or weakly polar have weak induced dipole interaction. Fifth is solubility. Alkenes like alkanes being either non-polar or weakly polar molecules are practically insoluble in water and other polar solvents but are quite soluble in non-polar solvents such as benzene, carbon tetrachloride, petroleum ether and weakly polar solvents such as ether. Sixth is density. The density of alkenes like those of alkanes increase with the increase in molecular mass till they have a limiting value of 0.89 gram per centimeter cube. Thus all alkenes are lighter than water. Next topic is hydrogenation and relative stabilities of alkenes. Alkene add on hydrogen in the presence of finely divided metals such as platinum, palladium or Rene nickel to form alkanes. This reaction is called hydrogenation and is used to determine the number of carbon-carbon double bond or triple bond in an organic molecule. For each double bond, 1 mole of H2 is absorbed. Mechanism: hydrogenation of alkenes or alkynes is a cis addition process as shown in figure 1.1. Here first H2 gets absorbed as hydrogen atom on the surface of the catalyst using its vacant d orbitals. This is followed by absorption of the unsaturated compound though its pi electrons. Therefore, transfer of adsorbed hydrogen atoms occur on the same phase of unsaturated carbon compound of alkyne giving cis addition product. The reduced product finally gets adsorbed from the surface of catalyst, leaving room temperature for fresh adsorption of H2 and the unsaturated compound. Heat of hydrogenation. Hydrogenation is an exothermic reaction and the amount of heat evolved when 1 mole of an alkene is hydrogenated is called its heat of hydrogenation. But but 1-ene, cis but 2-ene and trans but 2-ene all on hydrogenation give the same alkene, that is N-butane, but evolve different heat of hydrogenation. This means that these alkenes must have different inert energies and hence different stabilities. An alkene which has a lower heat of hydrogenation must have less inert energy and hence will be more stable than its isomers which have higher heats of hydrogenation. Thus, heat of hydrogenation of an alkene is a measure of its stability. The lower the heat of hydrogenation of alkene, more will be its stability. First, the unsubstituted alkene such as ethene has the highest heat of hydrogenation. Second, greater the number of alkyl groups attached to doubly bonded carbon atoms, more stable is alkene. In general, alkenes have the following decreasing order of stability. Out of geometric isomers, the trans isomers is slightly more stable than the corresponding cis isomer. Explanation for relative stabilities of alkene. The relative stability of different alkene can be explained on the basis of concept of hydroconjugation as discussed in unit 1. Next is alkene 1, 2, 3 or 4, 5 and 6 have 12, 9, 6, 3 and none alpha hydrogen respectively, and hence equal number of hyperconjugation structures can be written for each one of them. Since greater the number of hyperconjugation structure, more stable is the alkene. Therefore, relative stability of alkene follows the sequence 1, 2, 3, 4, 5 and 6. Since trans but 2-ene 3 is more stable than the cis but 2-ene, in which the two methyl groups lie on the same side of double bond and hence cause steric hindrance, therefore heat of hydrogenation of third is less than that of fourth. Next topic is chemical bonding. Next topic is chemical reactions. Alkenes are characterized by the presence of a double bond which consists of a strong carbon-carbon sigma bond and a weak carbon-carbon pi bond. The pi electrons form an electron cloud which lie above the below the plane of sigma bonded carbon atoms. These pi electrons are therefore more exposed and hence are less tightly held between the two carbon atoms. Since the electrons are negatively charged particles, therefore the pi electrons attract the electrophiles and repel nucleophiles. In other words, alkenes undergo electrophilic reactions. Now, in principle, electrophilic reactions can be of two types: addition and substitution. In electrophilic substitution reactions, one sigma carbon hydrogen bond is broken and a new sigma bond between one of the doubly bonded carbon atoms and the electrophile is formed. Since the bond energies of the sigma carbon hydrogen bond broken and the new sigma carbon halogen bond formed are not much different, therefore electrophilic substitution reactions are not accompanied by large energy changes. On the other hand, in electrophilic addition reactions, one weak sigma bond is broken and two strong sigma bonds are formed. The overall reaction is accompanied by a release of about 694 to 251, that is 443 kilojoule per mole energy. In other words, electrophilic addition reactions are energetically more favorable than electrophilic substitution reactions. Thus, the typical reaction of alkenes are electrophilic addition reactions and not the electrophilic substitution reactions. Besides these addition reaction, alkenes except ethylene undergo substitution reaction at the alkyl group. Some important reactions of alkenes are discussed below. First, addition of halogens. Halogens such as chlorine and bromine readily add to alkene to form 1,2-dihaloalkanes. During the addition of Br2 to alkenes, the orange-red color of bromine is discharged since the dibromo compound formed is colorless. The reaction is therefore used to test an unsaturation in inorganic compounds. Fluorine reacts with alkenes too rapidly to be controlled in the laboratory, while iodine does not react with alkenes at ordinary temperature. Thus, the order of reactivity of addition of halogens to alkene is fluorine, chlorine, bromine, and iodine. Mechanism of electrophilic addition reactions. Let us illustrate the mechanism of electrophilic addition reaction by taking the example of addition of Br2 to ethylene. The reaction occurs by a two-step ionic mechanism as discussed below. Step 1. Bromine molecule itself is non-polar, but when it comes close to an ethylene molecule, the pi electrons of double bond begin to repel the electron pair holding the two bromine atoms in the bromine molecule. As a result, bromine molecule gets polarized. The positive end of this bromine dipole behave as a electrophile and is attracted by the pi electrons of the ethylene molecule to form a pi complex, which subsequently gives the carbocation and the bromide ion. This step is slow and hence is the determining step of the reaction. Step 2. The carbocation formed in first step, being a reactive chemical species, immediately undergoes nucleophilic attack by the bromide ion present in the solution, forming the addition product. This step is fast and hence does not affect the rate of reaction. Evidence in support of the above mechanism. If the carbocations are really the intermediates in the above mechanism, then they should also react with the other nucleophiles when added to reaction mixture, and hence a mixture of products should be formed. This has indeed been found to be so. For example, when ethylene is bubbled into an aqueous solution of bromine containing sodium chloride, besides 1,2-dibromoethane, methane, 1-bromo, 2-chloroethane and 2-bromoethanol are formed. In the pi complex, there are no actual bonding between the ethylene and polarized bromine molecule. There is only electrostatic attraction. Limitations. The above mechanism involving the simple carbocation intermediates does not explain the following 2 points. First, stereochemistry of addition of halogens to alkenes. It has been observed that halogenation of alkenes always gives the trans dihalides and not cis dihalides whenever the product of the halogen addition is capable of showing stereoisomerism. For example, addition of Br2 to cyclohexene gives only trans 1,2-dibromocyclohexane. If the simple carbocations were the intermediates, both cis and trans 1,2-dibromocyclohexane should have been formed. This is due to the reason that carbocations are planar chemical species and hence attack the bromide ion on the initially formed carbocation 1 from the either face of the molecule, which is equally portable. Now next Next is reactivity of alkene towards electrophilic addition reaction. As discussed above, alkenes undergo electrophilic addition reactions. During these addition reactions, the attack of pi electrons of double bond occur on an electrophile, leading to the formation of carbocation intermediate. Evidently, rate of addition depends upon the stability of carbocation formed. Greater the stability of carbocation, more reactivity is the alkyne. In order to understand the reactivity of different alkenes, let us add an electrophyte and then examine the stability of carbocation forms. Since the stability of carbocation follows the order tertiary, secondary, primary, therefore 2-methylpropene, which gives us tertiary carbocation, react faster than but2-ene, but1-ene and propene, all of which forms secondary carbocation. These in turn react faster than ethene and forms a 1-degree carbocation. Although chloroethene gives a 2-degree carbocation, it is destabilized by negative I effect of Ci atom, and hence it is even less stable than primary carbocation. Therefore, chloroethane is least reactive. In general, the order of reactivity of alkene towards electrophilic addition reaction decrease in order. Second is addition of halogen acids. Alkenes react with halogen acids HCl, HBr, HI to form alkyl halides. The order of reactivity of halogen acids in the reaction is HI, HBr, HCl. This order of reactivity can be explained on the basis of bond dissociation energies of the halogen acid. The actual product formed, however, depends upon whether the alkene is symmetrical or unsymmetrical. First, addition to symmetrical alkenes. When the alkene is symmetrical, only one product is theoretically possible. Mechanism like the addition of halogen acids to alkene is also an electrophilic addition reaction and occurs in the following two steps. Second is addition to unsymmetrical alkenes. When the alkene is unsymmetrical, two products are theoretically possible. For example, the addition of HBr to propane in the dark and in the absence of peroxides can in principle give two products, but experimentally it has been found that the undergo these conditions, the major two product is 2-bromopropane and the minor product is 1-bromopropane. Next is Markovnikov's rule. Markovnikov, a Russian chemist, studied a large number of such addition reactions and postulated an empirical rule in 1869, which is known after his name as Markovnikov rule. The rule states that the addition of an unsymmetrical reagent such as HX, H2O, HOX to unsymmetrical alkenes occur in such a way that the negative part of addendum, that is adding molecule, goes to that carbon atom of the double bond, which carries lesser number of hydrogen atoms. Theoretical explanation of Markovnikov's rule: the addition of halogen acids to alkene is an electrophilic addition reaction. Thus, during the addition of HBr to propene, the first step involves the addition of a proton. This addition in principle can occur in two ways. If the proton adds to the terminal carbon atom of the double bond, a secondary carbocation is formed, and if the addition occurs on the middle carbon atom, as a primary carbocation is produced. Since a secondary carbocation first is more stable than primary carbocation, therefore carbocation is predominantly formed. This carbocation then rapidly undergoes nucleophilic attack by the bromide ion, forming 2-bromopropane as the major product. Thus, Markovnikov's addition occurs, though more stable carbocation intermediate. Rearrangement. Next topic is rearrangement during addition of halogen acid. It has been observed that the addition of halogen occurs to alkene via cyclic halonium ion, while the addition of halogen acids occur through the intermediate formation of simple carbocations. Since carbocations are prone to rearrangement, therefore if the structure of initially formed carbocations permits, it may undergo rearrangement either by 1,2-hydride shift or by a 1,2-methyl shift to form the more stable carbocation, which undergoes nucleophilic attack by the bromide ion to form the rearranged alkyl halide. Next is peroxide effect anti-Markovnikov's addition. It may be noted that Markovnikov rule is not always followed. In presence of peroxide such as benzoyl peroxide, the addition of HBr alkenes takes contrary to Markovnikov's rule. This is known as peroxide effect or Kharash effect. Mechanism of free radical addition. The addition of HBr to alkene in presence of peroxide occurs by a free radical mechanism. It consists of following three steps. Initiation. Second is propagation. It consists of two steps. During the first steps, a Br negative adds to double bond in such a way to give the more stable free radical. In the second step, the free radical thus produced Abstracts are H positive from HBr to complete the addition. Third is termination. Next topic is exceptional behavior of HBr. To understand why peroxide effect is observed with HBr and not with HCF, HCl or HI, let us consider delta H of two propagation steps. From the above data, it is clear that only with HBr both the steps are exothermic and hence the peroxide effect is observed. With HCl for HF, the peroxide effect is not observed because the second step involving the reaction of carbon radical with HCl or HF is endothermic. Further, the peroxide effect is also not observed with HI because the first step involving the addition of iodine radical to alkene is endothermic. Third is addition of elements of hypothallus acids HOX, where X is Cl, Br or I. Halohydrin formation. Chlorine and bromine in the presence of water readily add to alkenes to form the corresponding halohydrins. The overall reaction involves the addition of elements of hypothallus acid in accordance with Markovnikov's rule. Compounds containing halogen atoms and the hydroxyl groups on adjacent carbon atoms are called hydrogens. Next is oxidation of trialkyl boranes to alcohols. Trialkyl boranes obtained as above and oxidation within alkaline solution of hydrogen peroxide give alcohol as shown below. This overall two-step process is called hydroboration oxidation and gives alcohol corresponding to anti-Markovnikov's addition of water to alkenes. Stereochemistry. Hydroboration is in syn addition process, that is hydrogen and BH2 are added to the same phase of molecule. Seventh is oxymercuration reduction. Alkenes react with mercuric acetate Hg abbreviated as HgOAC2, where OAC is equals to OCOCH3 in aqueous tetrahydrofuran solvent to form adducts which upon reduction with NaBH4 in basic medium give alcohols. This two-step process is called oxymercuration reduction or oxymercuration demercuration and gives alcohols corresponding to Markovnikov's addition of water to alkenes. Mechanism. Oxymercuration is an example of electrophilic addition reaction and the mechanism closely resembles halohydrin formation. A cyclic ion called a mercurium ion is an intermediate state in which reaction. Next is comparison of hydration, hydroboration, oxidation and oxymercuration reduction methods of alcohol synthesis. As discussed above, all these three methods give alcohols. Hydration alkenes give alcohols corresponding to Markovnikov's addition of water to alkenes. Further, since this reaction occurs through carbocation intermediates, therefore, if the initially formed carbocation is less stable, it rearranges to more stable carbocation, thereby giving rearranged unexpected alcohols. On the other hand, hydroboration oxidation and oxymercuration reduction do not involve carbocation intermediates and hence always give expected products. Further, whereas hydroboration oxidation gives alcohol corresponding to anti-Markovnikov's addition of water to alkenes, oxymercuration reduction gives alcohol corresponding to Markovnikov's addition of water to alkenes. Thus, next is oxidation reaction of alkenes. Alkenes are readily oxidized from different products depending upon the nature of oxidizing agent. Some of important oxidizing agent of alkenes are discussed below. First is hydroxylation. Alkenes on treatment with the cold dilute 1% aqueous alkaline solution of potassium permanganate are oxidized to give vicinal or 1,2-diols or 1,2-glycols with KMnO4. It is itself reducing agent or MnO2. This reaction is called hydroxylation since during the reaction two hydroxyl groups are added across the double bond. During the reaction, the pink-violet color of KMnO4 solution is decolorized and a brown PPT of manganese dioxide is formed. This reaction is therefore used as a test of unsaturation under the name Bayer's test. Mechanism. Hydroxylation of alkene by cold dilute alkaline KMnO4 solution occurs by a cyclic manganate ester which upon hydrolysis gives a glycol. The Mn5 compound formed as a result of hydrolysis undergo disproportionation to Mn2 and permanganate ion. Stereochemistry. Since the reaction occurs though the intermediate formation of a cyclic manganate Therefore, it is a syn hydroxylation process, that is, the two hydroxyl groups are added from the same side of the double bond to give cis 1 2 glyalcohols. Next is oxidation with ozonization. When ozone is bubbled through the solution of an alkene in an inert solvent at a low temperature 196 to 200 Kelvin, it adds to alkene to form the unstable intermediates called molozonides. These intermediates then recognize to form the more stable ozonides. The reaction involving addition of ozone to alkenes is called ozonization. Ozonides are unstable and explosive compounds, therefore they never isolate, but they are decomposed in situ to form carbonyl compounds. The two methods commonly employed for the decomposition are reactive cleavage and oxidative cleavage. In the reductive cleavage, the ozonides are treated with a reducing agent such as zinc dust and H2O, or Zn and aqueous acetic acid, or H2PD, to form aldehydes or ketones with or a mixture of both depending upon the structure of alkene. Instead of ZnH2O or a catalytic hydrogenation, ozonides can more conveniently be reduced with dimethyl sulfide. A fine jet of CH3 whole twice S is directly passed through the reaction mixture. When the ozonide is reduced to the corresponding aldehydes and ketones, and CH3 is itself oxidized to dimethyl sulfoxide. Since DMSO is a water soluble and excess of CH3 whole twice S being volatile simply evaporates, therefore aldehydes and ketones are obtained almost in pure state. This two-step conversion of an alkene into an ozonide followed by its reductive cleavage to yield carbonyl compounds is called ozonolysis. However, if the ozonides are decomposed only with water, the H2O2 produced during the reaction oxidizes the initially formed aldehydes to the corresponding acids. Oxidative cleavage application. Ozonolysis is a versatile method for locating the position of a double bond in an unknown alkene, since no two different alkenes give the same combination of aldehydes or of ketones. Therefore, this method has been extensively used in the past for structure elucidation of alkenes. Next is substitution reactions. Alkene except ethylene consists of a carbon-carbon double bond and an alkane moiety in form of an alkyl group. Therefore, it is reasonable to assume that these alkenes can undergo two types of reaction, that is a free radical substitution reaction characteristics of alkane, second a free radical addition reaction characteristics of alkenes. The actual reaction will depend upon the choice of conditions as discussed below. First, free radical substitution at the allylic position. When propane is heated with chlorine or bromine at a high temperature of 773 Kelvin, the halogen atom at the allylic carbon, that is carbon atom next to the double bond, is substituted by a halogen atom forming allylic halides. Such a reaction in which halogenation occurs at the allylic position of an alkene are called allylic halogenation reactions. Allylic chlorination can also be carried out by treating an alkene with the sulfuryl chloride at 475 Kelvin in presence of light and traces of organic peroxides. Mechanism: at high temperature, halogen molecule undergoes homolytic fission yielding halogen atoms, which abstracts a hydrogen from the methyl group to give a resonance stabilized allylic radical. The allyl radical in turn react with the other molecule of halogen to form 3-halopropene and a new halogen atom. Next is free radical substitution versus free radical addition. It is surprising that under conditions of high temperature, alkenes undergo free radical substitution by halogen atoms, but in presence of peroxides, the halogen atoms undergo free radical addition across the double bond. To account for this, it has been suggested that at high temperature the addition reaction become reversible, that is halogen atom adds to propene to form intermediate radical, but due to high temperature it is expected reversibly before the intermediate radical and can add other halogen to form addition product. Further, because of the low concentration of halogen, the intermediate radical will have to wait for a long time before it collides with the halogen molecule, and hence it prepares to revert to the starting material. On the other hand, the allylic radical generated as a result of hydrogen abstraction by the halogen atom can wait for the collision with the halogen molecule because of its greater stability due to resonance. Next is allylic bromination. A specific laboratory reagent for allylic bromination of alkyls is nitrogen bromosuccinamide (NBS). The reaction is catalyzed by light. Mechanism: NBS acts simply by providing a constant low concentration of bromine, thereby favoring the substitution reaction and preventing the addition reaction. Second is electrophilic substitution reaction at vinylic position. Although electrophilic addition reactions are characterized of alkene, they may also undergo electrophilic substitution reaction at the unsaturated carbon atom. For example, when an alkene is treated with an acid chloride in presence of anhydrous AlCl3, it undergoes Friedel-Crafts reaction to afford alpha beta unsaturated ketones. Mechanism: step 1. If in presence of anhydrous AlCl3 acids, chloride generates the selenium ion, which adds to the double bond to form carbocation intermediate. Step 2. The carbocation is produced may lose a proton, forming a alpha beta unsaturated ketone. Alternatively, the carbocation may accept a chloride ion, form AlCl4, forming an addition product which subsequently loses a molecule of HCl to form alpha beta unsaturated ketone. Next topic is industrial applications of ethylene and propene. First, industrial application of ethylene. Ethylene is mainly used in the synthesis of polyethylene ethylene oxide, vinyl chloride, and styrene. Second, ethylene is also used in manufacture of ethanol, which is an important beverage and an excellent industrial solvent. Ethylene is also used in the manufacture of many useful chemicals such as acetaldehyde, acetic acid, and ethyl acetate. Ethylene oxide is used in the manufacture of ethylene glycol, which is used as an antifreeze in car radiators and also in manufacture of polyester fibers glycol. Fourth, both vinyl chloride and styrene upon polymerization form polyvinyl chloride and polystyrene, which are extremely useful polymers. Second is industrial applications of propane and propylene. Propylene is mainly used for the manufacture of propylene, which is extensively used in making automotive molding, seat covers, carpet fibers, ropes. Second is oxidation of propylene gives acrylonitrile, which is widely used in the manufacture of Orion and acrylic fibers, which are used for making clothes, carpets, and blankets. Third, propylene is also used in the production of cumene, which is widely used in the synthesis of two very important industrial chemicals such as acetone and phenol. So this was all from this chapter. I hope you all like it. Thank you so much for watching this.